to lectures on digital electronics. We are discussing the sequential logic circuits design. In the previous class, we have discussed the shift resistors, and now let us continue with the introduction of counters in this lesson. So, objective of this lesson is the counter. What is the counter? And we will see the types of the counter and the difference between synchronous and asynchronous counters and working of ripple counters. So this is the objective of this lesson. Before starting this, we have to discuss some of the topics that are left. So that is PIPO left shift resistor and universal shift resistor, and comparison of combinational and sequential logic circuits that we have to complete, and applications of the resistors also we have to complete. So those topics will be covered within few minutes, and we will continue with our main objective of this lesson. Thank you. So this is the PIPO left shift resistor. In this you have the control signal shift or load bar, that is the circuit will shift left whenever the control signal is 1. Whenever the control signal is 1, then it will shift left like this. Each bit is shifted left like this. And if first loading of the data is done, the loading of the data is done whenever this control bit is 0, then the data bits B0, B1 to Bn data bits are loaded into the resistor, shift resistor like this. So after loading of the data, to shift the data, the control signal must be 1. Then what happens is the data is shifted left like this. Like this. So the data shifting is done. So this is the n bit parallel in parallel out left shift resistor. Now let us consider universal shift resistor, which is widely used, 74194. It is the IC number of the universal shift resistor. It can shift left, shift right, and parallel out, etc. So it can do such jobs. So let us see. The universal shift resistor is a reset. When the master reset, input goes low. The synchronous operation, the universal shift resistor is reset when the master reset input goes low. The synchronous operation of device is determined by the two mode selector inputs. S0, S1 will decide the mode selection of the bits. So it has serial and parallel inputs. So when S0 is high, S1 is at low, then shift left operation is done synchronously with the positive edge of the clock. In this mode, the serial data is entered at the shift right serial input mode. So when S0 is at low and S1 is at high, then shift left operation is done in synchronous with the clock. In this mode, the serial data is entered at the shift left serial input. When both S0, S1 inputs are at a high, parallel loading operation is done in synchronism with the positive transition of the clock. The 4 bits of the data are applied to the parallel inputs. So when both the S0, S1 inputs are at low level, then we have inhibit clock operation. In this mode, the operation will inhibit the shifting of data in the shift register. So let us consider this is the mode selection. Okay. For 1 1, it is the parallel load. The data is loaded into the shift register parallelly. For 1 0, it is the shift right operation. For 0 1, it is the shift left. For 0 0, it is the inhibit operation. So this is the truth table of universal shift register. That means whenever it is reset clock pulse is low, that is master reset is 0, then the flip flop whatever may be the activities on the clock and control bits, mode selection bits, and shift right, shift left, and what happens is the flip flop is cleared. That is from Q0 to Q3, all the status bits outputs of the flip flops is cleared whenever it is reset. And next, whenever it is high, and whenever the data inputs, that is if there is no clock pulse at all, then the flip flop that is the shift register, universal shift register, holds its previous values only. Next, shift left operation, and in the shift left operation, the mode bits are set accordingly. S1 is 1, and the clock, whenever for each clock event, how the data is shifted, you see the Q3 is because it is shift left, the Q3 bit how it is loaded with 0, if you see. And the next, shift right operation, that means whenever the mode selection bits are S0 is 1, then what happens is the bits are shifted right, that is Q0 is loaded with 0, and the next bits are shifted right, succeeding bits of flip flops. And the parallel load for 1 1, the parallel load operation is done. That is the data of bits are loaded into the flip flops. D0, D1, D2, D3 are loaded into the flip flops. So this is already I have told you. So this is a logic diagram of universal shift register. You see, with the help of this gate circuitry, we are able to, with the help of this gate circuitry, we are able to do all these operations, setting the mode bits accordingly, enabling the corresponding AND gates, and thus loading the parallel data or shifting left or shift right. So these all operations can be performed with the help of this universal shift register. Observe here, these are the mode selection bits, and with the mode selection bits we are able to, and the master reset bit is also there, and that master reset bit, this is the master reset bit, and with this the data how it is cleared, and how with the help of mode selection bits how the actual data, this is the data bits, how they are loaded into the flip flop, you can observe. This is the D0 bit is loaded into this, D1 is loaded into this, D2, D3 loaded into this. And after that, based upon the mode selection, left shift or right shift, the data may be shifted left, or it will be shifted right. So this is the timing diagram of universal shift register. So based upon the mode control signals and master reset bit clear and mode control signals, so we are able to shift the data into the out flip-flops by applying the data here, and the shifting is done whenever corresponding bits of mode control bits S0 S1 changes. So let us see the applications of shift registers. The main application of shift register is temporary storing of the data and a data transfer, left shift or right shift from one register to other registers, one memory device to other memory device, and a data manipulation. That means the data can be manipulated, that is shift left or shift right, and these registers also can be used as counters, and the shift register used as a parallel to serial converter. That means which converts the parallel data into serial data. It is utilized at the transmitter section after analog to digital converter of ADC block. In the communication, the transmitter, before transmitter, the analog message signal is converted to digital, so the digital data is available in the parallel format. That formal parallel format is converted into serial, so that the transmitter will transmit this data into space. Thus this is the application of the shift register. And shift register is used as a serial to parallel converter also. That means which converts the serial data into parallel data. It is utilized at the receiver section before digital to analog converter. That means at the receiver section, from the space, the receiver will receive the electromagnetic wave, so which is converted to electrical signal and message signal, and that is demodulated, and actual message signal is detected. After detecting that message signal, it is converted into uh, digital analog to digital data, analog to digital. That means DAC, digital to analog data. Okay, that analog signal is once again it is processed, and then it is sent to DAC block. Okay, so that is a serial to parallel conversion. Next, the shift register along with some additional gates generate the sequence of zeros and ones. Hence, it is a sequence generator, and they can be used as counters also. So D flip flops may be used, or T flip flops may be used. The group of T flip flops or D flip flops is used to, so that sometimes D flip flop is used as a ring counter or Johnson ring counter, and while T flip flops or group of T flip flops are used as counters. So shift register 8 bit, we have like this, that is SN74595. It is a shift register, 8 bit shift register. ICs, this is the TTL ICs, and the CMOS ICs we have. And you see TTL IC shift register is 74595, and CMOS ICC is CD4014, and 74194 is the universal TTL shift register, and other 195 is also available as a universal shift resistor. So these are the few IC numbers of TTL and CMOS of shift resistors. And let us see the comparison between combinational and sequential circuits. In this, its output is determined by the present values of inputs only. That is the combinational circuit. And the sequential logic circuits, it is output is determined the present values of the input as well as past values of the output. Second point, it does not have a memory. Combinational circuit does not have memory. And in the sequential circuit, we find yes, memory plays important role, and there is a feedback path from output to input. And the next, the combinational circuit can be described with the help of the truth table operation, but here the sequential circuits, its operation can be described by truth table and a timing diagram. So that is additional description logic we have to use, that is the timing diagram. And next, the combinational circuit does not have clock signal, whereas sequential circuit clock is very important. Without clock signal, the sequential circuit does not perform sequential operations. Next, combinational circuit is a simpler one, but the sequential circuit design is complex, and the circuit is also complex, and design procedure is also complex. And next, it built the combinational circuit is implemented with gates such as not and or and or like that, but the sequential circuits are built with gates and combinational circuits. So that is the requirement. And examples, let us see the combination circuits we have discussed: adders, subtractors, parallel adder, serial parallel adder, and two complement parallel adder subtractor circuits. And in the sequential logic circuits, we have the examples: flip flops, counters, and shift resistors. So this is the comparison we can do between combinational and sequential logic circuits. So with this, we completed all shift resistors, and now let us continue with counters. In this class, we discuss the counter, and we'll see types and ripple counters. And now let us see the counter is a register which has the capability of counting the number of clock pulses that have arrived at its clock input. So that is the definition of the counter. And counters, flip-flops connected together to perform counting operations. So gates in a counter are connected to produce prescribed sequence of binary states in register. So n number of flip-flops may count pulses up to 2 power n. So modulus of a counter. So the number of states are called modulus of a counter. So n number of flip-flops may count pulses up to 2 power n. So mode 3, that means modulus 3 counter. That means this counter will count up to 3 clock pulses. That is the mode 3. Like this. Like this. This counter counts 0, 1, 2, 0, 1, 2, 0, 1 2 like this. This mode 3 counter will count to only 3 pulses, and mode 5 counter will count like this: 0 1 2 3 4 0 1 2 3 4 0 like this. Mode 5 counter. So the counter counts only 5 pulses, mode 5. So mode 16 will count from 0 to 15. Mode 10 counter counts from 0 to 9. So this is the modulus of counter. Next, modulus n counter can be called as divide by n counter. That is, modulus of the counter is the number of output states of the counter. N stage counter will have 2 power n states. If a counter has to count n pulses, which is not a power of 2, then we have to consider a divide by factor which is same as the modulus. So the counters which involve this factor are known as divide by n counter. So now to construct these counters, we have to start with a ripple counter of n flip-flops. At the count of n, all the flip-flops must be reset to 0 by adding a feedback gate in the circuit. Such feedback gate is provided by a AND gate or NAND gate, in which the output provides all the clear inputs in parallel. So the flip-flops outputs of the counter are connected to the inputs of the NAND gate. So divide by n and modulus n. These names are very clear to you, I hope. So now let us see the types. Asynchronous counters, these are also called ripple counters. Synchronous counters, and let us consider asynchronous and synchronous counters differences. So asynchronous, first flip-flop is clocked by external clock pulse, first flip-flop, and each succeeding flip-flop is clocked by the Q output of the previous flip-flop. This is an important point. Hence it is called asynchronous. Whereas in synchronous counter, clock input is connected to all of the flip-flops and hence clocked simultaneously. That means clock is applied simultaneously to all the flip-flops. And the synchronous counter is slow compared to asynchronous counter is slower one compared to synchronous counter. Synchronous counter is the faster one. And serial counters, asynchronous counters are called serial counters, and the synchronous counters are called parallel counters. Here in the asynchronous, the cumulative propagation delay is more. In the synchronous counter, propagation delay is less. Now asynchronous counters, let us consider ripple counters, is consisting of, let us consider 4 flip-flop. Let us consider a simple ripple counter here. This is the ripple counter. So always remember that if you use JK flip-flop, all the JK inputs of each flip-flop is shorted like this. 2 JK, both are shorted. You see, both are shorted, and all these shorted inputs are connected to logic 1. This is the important one. That means we are placing the JK flip-flop in toggle mode. So always the counter needs to be configured in toggle mode only to make it as a counter. That you have to remember. Number one. Number two, another important observation you have to make is the first clock, main clock input. This is the clock. So the main clock input is applied to first flip-flop, that is FF0, and the next succeeding flip-flop receives the clock from the output of the previous flip-flop. For example, the Q0 is the output of FF0. This Q0 is applied as a clock input to the next FF1. Similarly, the Q1 is the output of FF1. It is the output of the FF1, and this same Q1 is applied as clock input to the FF2. Similarly, the Q2 output, FF2 output is the Q2, which is connected as a clock input to the FF3, like this. So you have to connect. That means the main clock input is applied to only first flip-flop. All other flip-flops are taking previous flip-flops output size clock signals. So this is the always remember the first flip-flop FF0 is the LSB and FF3 will be the MSB bit. You have to treat, that is Q3 is MSB, Q0 is the LSB bit. So this all we have discussed how the first flip-flop FF0 receives the main clock, and next flip-flops how they are receiving clock inputs as previous FF's outputs. So now another important thing is, instead of JK you can use T flip-flop also. You can use T flip-flop also. For example, let us consider here. For example, a 2-bit T flip-flop, 2-bit counter. For example, 2-bit counter I am taking 2-bit or 3-bit. Let us take 3-bit counter. This is the T0 input, T1, T2. All these T0, T1, are shorted together and applied with 1, that is connected to logic 1. So this is the condition for T0. If you use T flip-flops, this is the way of connecting. And each output, this is the Q0 output, Q0. You have to connect Q0 as a clock pulse. So the main clock input is applied to the first flip-flop, and output of each flip-flop is connected as a clock input to the next flip-flop. So this is the clock inputs. This is Q1, this is Q2. So like this, if you use T flip-flops, you have to make connections like this. If you use a T flip-flop, circuit connections also very simple, and the clarity diagram. Let us see the operation. Each flip-flop will toggle when its clock input receives a negative edge, because negative edge triggering clock pulses are used. Negative edge triggering flip-flops are taken into consideration. So this is a output q, and initial output is q equals to 0 0 0. Q0 toggles per each negative clock edge, hence it receives each clock pulse. The remaining flip-flop toggles less often because they receive their clock signals as from the previous outputs of previous flip-flops. Now, let us see the states of asynchronous counters. So, for each pulse, you see, for each pulse, the Q0 toggles. Q0 toggles. Observe here, for input pulse 0, this is the initial one 0 0 0. Next, for first pulse 0 0 0 1, for second pulse 0 0 1 0, next third pulse 1 1, for fourth pulse 1 0 0, for fifth pulse 1 0 1, like that up to 15. At the 16th pulse, again the flip flop is initialized to zeros. That means the counter counts 16 pulses, 0 to 15, 16 pulses it counts. So the counting sequence is like this: 0 0 0 0, 0 0 0 1, 0 0 1 0, 0 0 1 1, like this. The state diagram, this is a state diagram of counter. For each pulse, for the next pulse, it goes to 1 1 1 0. For the next pulse, it goes to 1 1 1 1. This is the 16th pulse. Now, at the 16th pulse, the counter initialized to zeros. So, the Q0 changes state at the falling edge of each clock pulse. All other Qs change when the output of the preceding flip-flop changes from 1 to 0. This negative transition ripples through the counter from LSB to MSB. So, you see the timing diagram of asynchronous counter. You see the main clock input is this. This is the main clock input. And for each negative transition, that is negative edge, that means, for example, you have to observe this negative edge only. In this negative edge, we have draw a dotted line like this. You see, dotted lines are drawn. You see, dotted lines for each negative edge dotted lines are drawn. Like this, you have to observe, and after that, because this main clock is applied to first flip-flop FF0, hence because FF0 is configured in toggle mode, that means it complements its previous outputs for every clock activity, for every clock event. The FF0 is complements its previous output. So let us consider the previous output of the Q0 is 0. Initially, all the flip-flops outputs are initialized to zeros only initially. Okay. Next, so let us consider the first edge comes to FF0. FF0, first edge. When the first edge comes, negative edge, there is a clock event, hence the FF0 will complement its previous output. That is, 0 is complemented to 1. This 0 is complemented to 1. And next, at the next edge, that is second pulse, at the next second negative edge, this 1 is once again complemented to 0, like this. It is 0. In the next edge, third, at the third pulse, third negative edge, this 0 is complemented to 1. This is 1. In the next edge, this 1 is complemented to 0. And this 0 is complemented to 1. Like this, for each edge, negative edge, it is complementing its previous output. So I hope you clear. The first flip-flop timing diagram is clear. Now let us see FF1. After drawing first Q0 diagram, let us go for Q1. Now observe here. The FF1 flip-flop receiving clock is Q0. This Q0 will act as, this Q0 output of FF0 act as clock to the FF1. To the FF1. That means each negative edge of this act as a clock event to the FF1. Each negative edge of this acts as a clock event. That you have to remember. So now observe here, there is a negative edge here. Hence, Q1 is complementing its previous output. Previous output is 0 and it is complemented to 1. Next negative edge. This is the next negative edge. Hence, the 1 is complemented to 0, like this. In the next negative edge, this 0 is complemented to 1, like this. For each negative edge, it is complementing its previous output, like this. So the Q1 diagram is also, timing diagram also, it is clear for you, I hope. Next, this Q1 signal acts as a clock to the FF2. That means each negative edge of this Q1 will activate the FF2 flip-flop. So now let us see, this is the negative edge. The Q2 is 0 up to this negative edge. Once negative edge is there, the Q2 complements its previous value 0 to 1. In the next edge, it complements to 0. The next edge, it complements to 1. Like this. The next edge, it complements to 0. Like this. So this is the next. This Q2 waveform acts as a clock signal to the FF3. That means each negative edge will activate the FF3. So this is the negative edge. This negative edge will activate the FF3 flip-flop. Hence, this 0 is complemented to 1. And this negative edge will activate, hence it complements 1 to 0. Like this. So this is a timing diagram of this counter. Now let us see 3-bit asynchronous up-down counter. A counter may count up or count down depending on the input control signal. Because of limited word length, the count sequence is limited. For an n bit counter, the range of the count is from 0 to 2n minus 1. That count sequence usually repeats itself. When counting up, the count sequence goes in this manner: 0, 1, 2, up to 2n minus 1, and next 0, 1, 2, etc. When counting down, the count sequence goes like this: 2n minus 1, 2n minus 2, and so on up to 2, 1, 0, like this, and next 2n minus 1, 2n minus 2, and so on. So this is the way of working of up down counter. Let us consider 3-bit asynchronous up down counter. Here, if you observe, this is the mode control bit, that is the control bit, and JK flip flops are taken, and each JK inputs are tied to 1. They are connected to logic 1 like this. Each JK is connected to logic 1. That is the basic connection. Always you have to remember, because each flip flop is to be configured in toggle mode only. And observe here, the first flip flop is taking the clock input. The first flip flop is taking the clock input, and each flip flop is the negative edge triggering type, because for the negative edge triggering you have bubble and arrow mark like this at these positions. You see, negative edge triggering flip flops we have taken. Next, observe here a gate combinational circuit here structure: 2 AND gates, 1 OR gate. Let us consider this gate structure. This is the important gate structure which facilitate us to make this counter as up counter or down counter. We can configure with the help of this control signal and gate structure. These gate structures make the counter as up or down. How? Let us see. Observe here. For example, the mode control bit, if it is 1, if the mode control bit is 1, output of NAND gate is 0. NOT gate is 0. Output of NOT gate is 0. This 0 is connected to going to all the upper AND gates, disabling upper AND gates, and this 1 is going to down AND gates, all the down AND gates. So these AND gates are enabled whenever mode control 1 is there. Down AND gates are enabled, and up AND gates are disabled. That means, you observe here, the QA output. That means one important thing you have to remember is, for example, here one flip flop is there, here next flip flop is there, because each flip flop is having Q outputs, Q bar outputs, complementary outputs. If you connect this Q as a clock signal to this, then it will act as up counter. Instead of that, if you connect Q bar output, here Q bar output is there, instead of this, if you connect Q bar output like this to this clock of this flip flop, then it will act as down counter. It will act as down counter. This is the important point you have to remember. Hence, observe here, the Q outputs are connected through upper AND gates like this as a clock input, AND gate and OR gate. Q outputs, you see, AND OR gate, through AND OR, it is going to clock input of next flip flop. This is for the purpose of up counting. Next, observe here the down AND gates. The Q bar outputs are connected through AND or to clock input of next flip flop like this. Q bar output through AND or it is connected to clock input of next flip flop. That means for the purpose of down counting. Okay, so that means this gate circuitry facilitates and this control signal facilitate us to configure this counter as up or down. Let me tell you one example out of this. Now let us see the gate structure, how it is facilitate us, gate and control signal, how it facilitate us. These are AND gates. This is the OR gate. So each AND gate, for example, this Q is coming here, here, Q bar is coming. Let us see the control signal M. For M equals to 0, M equals to 0, let us see. For M equals to 0, what happens? The output of NOT gate is 1. That means this AND gate is enabled. Hence, the output of this AND gate is Q. And next, let us see. This M equal 0 means here 0. Output of this AND gate is 0 only. 0 Q bar, both are inputs to this AND gate. So 0 dot anything is 0. So what is the output of OR gate? Q. So this Q is going to next flip flop, succeeding flip flop. Because whenever Q is going means whenever Q is going, then the counter counts up, because the counter is configured as up counter like this. Let us consider, for example, instead of 0, if you apply control bit 1, let us see 1 is applied. This is 0 is not, but 1 is applied. When 1 is applied, the output of NOT gate is 0. And 0, what is the output of AND gate? 0 dot Q is 0 only. It is 0. And this M equals to 1 means here 1, here 1. That means this AND gate output is 1 dot Q bar is Q bar. So what is output of OR gate? Q bar. That means Q bar is going as a clock input to the next flip flop. Hence, it is configured as down counter. Whenever you apply Q, it will act as up counter. Whenever you apply Q bar, it will act as down counter. So this is the important gate combinational circuit which will enable us to configure the counter as up or down like this with control bit and gate circuitry. Hence, we are able to configure this counter as up or down counter. So this is the sequence of counting up and counting down from 000 to 111, 0 to 7. This is the 3-bit counter, means it is 000 to 111. So it count up to 8 pulses. Mode 8 counter. It is called mode 8 counter. So down counting also from 7 to 000. So with this, we conclude our lesson, and in the next class we will continue the working of timing diagram of this counter. We will see and continue with the class. Thank you.